I think I forgot to record all that for those who didn't make it to class. Well, or for any of you who want to look later, sorry. So my recording was off, so I'll say there's that, and there's that. All right, that's all the video gets. On we go. All right, so r equals 3 sine theta. So we're going to do some symmetry tests. In fact, let me just give you can tell I'm much more dependent on the book at this point because I hardly ever do this. So let's go back to, I'm going to give you 3 symmetry tests on this that they're going to have us go through. Okay, so how do we go through that? So first one, number 1, symmetry with respect to the polar axis. So polar axis, what is the polar axis? Well, we call it's the x-axis, really. We're just in the polar world now. So we're calling the x-axis the polar axis because it's where we start. It's 0. So basically, a graph is symmetric, same, on the 2 sides of the polar axis, the x-axis. Meaning, like, if the graph has something up here and down here, that would be symmetric, same, on the top and the bottom of the x-axis. This is the polar axis, the x-axis. So how do you know if it has that? You replace theta with negative theta, simplify, if result same as original, it's a yes. It has polar axis symmetry. So that's the look of polar axis. So what we're doing to help us graph, rather than just plugging in a bunch of points, r theta, and just plug everything in the world in, we want to determine if graphs have that kind of symmetry. So number 2, we want to test symmetry with respect to the line theta equals pi over 2, which if you think about it is the y-axis. We're just saying it in polar talk now. Am I going too quick? You get that first one down? So you replace theta with negative theta, simplified. If it comes out the same as the original, yes. That's how all these are going to work. You're going to replace something with something, simplify, and see if you come out the same as the original. That's how you test. And I'll explain why that's true in a minute after we kind of get it all down. In fact, let me actually write it right on here. It's because if positive theta, whoops, that's a theta there, and negative theta have the exact same points always, then the graph is the same above and below the x-axis, above and below the polar axis. They call that the polar axis when you're in the polar world. Let me let that sink for a minute. Did you understand that? Right? Some graph is the same above and below, up here above and below the x-axis, the polar axis, if whenever you go up some angle, any angle, 30 degrees, whatever, and you go down 30 degrees, you got the exact same picture. That's what it means to be the same above and below the polar axis, the x-axis. Positive angle, negative angle, same thing. So, for example, if I had, what's one of those that would do that? Probably better wait, or I guess I could, let's just wait. We'll get there in a minute. But positive and negative, well, actually, no, there might be an easy one. Yeah, cosine. Yeah, remember how we already saw back here from the picture? Right here, remember this? Cosine, where am I at? Right here, the cosine is That one's clearly got polar axis symmetry, doesn't it? That circle, the cosine circle, is the same above and below the x-axis, isn't it? Whereas the sine graph is not. There's not the same stuff above as there is below. There's nothing below. So the sine does not have polar axis, x-axis symmetry. It's not the same above and below the x-axis. The sine is not. But the cosine is. This is the same above and below the x-axis, right? Well, why is that the case? Because if you take that equation, if you take something like y equals cosine theta, and you plug in any positive angle, plug in whatever you want, plug in positive 30 degrees, and what do you get? Y equals cosine of positive 30, and then you plug in negative 30, you're going to get the same answer. Cosine of positive 30, if you go to the unit circle, what is that? 30 at root 3 over 2, and this is also root 3 over 2. It's going to come out the same, exactly the same. In fact, you might remember we even learned cosine's an even function, and it lets the minus come to the front or vanish. Anyway, I don't mean to bug you with properties you might not be familiar with. You go to the unit circle, both these are the same answer. That's the point. If you plug in a positive angle and a negative angle, and they always come out the same, right? Meaning if you replace theta with negative theta, so that way I'm not just putting in 30 for negative 30, or negative 30 for positive 30. I'm putting in negative theta, which could be any angle for the original theta, and it comes out the same as the original, meaning that negative did nothing different. That means all negative angle results are the same as all positive angle results, meaning everything below is the same as everything above. That's what proves it. You see why that test really verifies it? Now, having said that, if it fails the test, here's the weird part, which was surprising to me. I didn't remember. It's been a long time since I've done this. You don't really do much of this in higher math. You do a little bit of it, and you don't actually graph polar though. You use polar coordinates in calculus, but you don't actually graph the limicons and all that hardly again. So that's why I don't have much deeper knowledge of it. Anyway, this was a surprising result to me. If you plug in, the theta, negative theta, and it comes out the same as the original, then that's a yes. If not the same as original, so if you plug in negative theta for theta and it comes out not the same as the original, I would have thought that means, well, then it doesn't have that symmetry. But in reality, that means no conclusion. In other words, it may or may not have it. In other words, you can fail the test and it might still have it. That's weird. That's not what we're used to, huh? Normally, hey, if it comes out the same, it's a yes. If it doesn't, it's a no. For all three of these tests, so hear this. If you do the test and it's the same as the original, all three are going to be, plug in this, see if it's the same as the original. If you do your thing and it's the same as the original, then yeah, that's a for sure yes. But if it comes out not the same as the original, that's not a for sure no. That's a, we don't know, may or may not. Now, how could that be? If it's coming out different than the original, then it's different above and below, right? Maybe not. See, the trick is with polar, you can go around more than 360. And you could actually make it the same another way by going more than 360, not just by positive and negative. There's other tricky ways to make it the same. So that's a deeper thing that I hadn't thought about at first. I didn't remember until I read the book. So everybody tracking with me on that. So this is a positive test only. So it's like one of those medical tests where they can verify something that's going on with you, but they can't rule it out. Right? That's kind of like what all these tests are. If they pass the test, if after plugging in negative theta in the place of theta, it comes out the same as the original, then it's a yes. If it doesn't, it's a we don't know for sure. Could be yes, could be no. Inconclusive. All right, you got it. I beat that drum enough. Let's go on to number 2. Next thing is we want to say, okay, y-axis. Y-axis is this axis. That's the line theta equals pi over 2, right? This is the pi over 2. If you turn the cannon to 90 degrees, that's the cannon facing 90 degrees, pi over 2, isn't it? So that's how we say y-axis in the polar world. Theta equals pi over 2. So what do we do? We replace, again, we're always replacing. Replace r theta with negative r, negative theta. So replace both of them this time. Not just the negative theta. Replace both of them and, simplify, same kind of thing. Simplify, same as original, then it's a yes. So this test is replace both r and theta with negative r and negative theta and simplify, and if it comes out the same as original, it's a yes. If it's no, it's a we don't know for sure. That's what these three tests are going to be, by the way. One of them is going to be negative theta for theta. One of them is going to be both. The other one is going to be just r for negative r. Those are going to be our three tests. So just the theta, just the r, or both. This one's the both. And that, if that's the case, that will mean the graph is the same right and left of the y-axis. Why? Why would that make a graph the same to the right and the left of the y-axis? Well, suppose you had a graph like sine. Remember that sine one we just did? We just looked at? The sine circle back over here, right? This one, right? That one's certainly the same on the right and the left of the y-axis, the theta equals pi over 2 line, right? So that one's going to have that kind of symmetry. So what does that mean then? Well, that means if you're at any point, let's say right here, r theta, if instead of that moving the cannon to that positive theta, you move the cannon to the negative theta, you with me? Right, we're saying instead of going up and hitting a point at r, turn the cannon to theta, shoot out r. Instead, turn the cannon to negative theta and shoot what? Negative r. Shoot backfire. Backfire, negative r, you get the same point. Do you see that? That's negative r, negative theta. And if you get that point, then you're getting points on that are same on right and left of the y-axis. See how that works? That's a way of testing that. Both of them, negative r, negative theta. And again, if it's not the same, then it's just inconclusive. Good so far? One more test of symmetry. Number 3, the third test of symmetry is pole symmetry, or in other words, origin. That's what they call the origin in the polar world. They're just saying, all right, so you've got the actual, we call that origin symmetry. I don't know if you've seen these kind of symmetries before. Symmetry to the origin. You go over these again in pre-calculus. I mean, not for polar stuff, but just for XY stuff. So anyway, something is the same across the origin if you replace, what do we have left? We did theta alone with negative theta. We did r and theta with negative r, negative theta. So what do we have left? R alone with negative r. Simplify. Same as original. Same as original, yes. So there it is. So this is just r with negative r. So yeah, and origin symmetry, that one's a little weirder to see. That would be a graph that does something like this and like this. So you might not even have ever thought about what origin symmetry is. That means as you shoot through the origin to the other side, the graph is the same. So say you're right here. Take any point you want. Shoot through the origin, same distance to the other side. Is there a point there? Yeah. Then that graph has origin. Take any point you want. Take this point. Shoot through the origin, same distance other side. Boom. Yep. There it is. That's called origin symmetry. When shooting through the origin to same distance to the other side, it always produces, all these points, shoot through the origin, produce all these points, same distance other side through the origin. That's called origin symmetry. And how do you shoot through the other side? If this is r, then you just shoot negative r, don't you? Backfire r. That's why that proves it. All right, we got the 3. Are you ready to use them? So let's go back to our actual question now. So here we are. They're giving me r equals 3 sine theta. They want me to do the 3 tests. So first test, is the polar equation symmetrical with respect to the polar axis? Polar axis is the x-axis. How do we do that test? Negative theta. plug in negative theta. So let me take the equation, 3 sine negative theta. Or here, I'll just do it over here. R equals 3 sine negative theta. So I plugged in the negative theta. That's the x-axis test. So what do we do with that? What do you do with sine of negative theta?
You can move the negative to the front.
Good, yeah. I probably should remind you at this point of the negative rules when it comes, the negative plug-in rules when it comes to sine, cosine, tangent, all the trig functions. Yeah, for sine and tangent, and they're upside downs, but we don't really care right now. Cotan and cosecant, whatever, who cares? But it's true. For all those, if you plug in negative theta, the negative goes to the front. You're allowed to take the negative to the front. Whereas for cosine, and of course his upside down secant, if you, even better, if you plug in negative theta, the negative vanishes. You can just cancel out the negative completely. That's because he's an even function. Have we talked about even and odd functions? A little bit, yeah. Because, yeah, sine, so I'll just write that again if that helps you, is an odd function. Sine and tangent, and their reciprocals. Cosine is an even function. Even functions, the negatives plugged in vanish. Odd functions, they come to the front. You'll talk more about that in pre-calculus. Okay, so just remember. So the main thing to remember from all that, you don't need all the names and everything. Just sine and tangent, negatives to the front. Cosine, negative vanishes. So negative in a sine comes to the front. So I get negative 3 sine theta. You guys with me so far? So what am I doing, and what does this mean? They want me to test for polar axis, which is the x-axis, which means plug in negative theta. I plugged in negative theta, and for sine or tangent, you're allowed to pull the negative to the front. For cosine, it just vanishes. So I pull the negative to the front, and then is this the same as the original? That's the question. After our simplifying was just pulling that, remember it said simplify, plug in, simplify. My simplify was just simply pulling that negative to the front. Now ask, is this the same as the original, question mark? No, the original had no negative in the front. No, it's not the same. It's got to be exactly the same as the original. The original was positive 3 sine theta, right? So no. So we go over here and we choose no. No, we don't. No, we don't choose no.
You don't choose no, you do the may or may not.
May or may not, right? Everybody with me? Remember, that's the whole point. May or may not. This is a positive test only. You can't rule it out. It's like going to the doctor and saying, I think I've got mono. Well, then they test you and they say, yep, you've got it. Or they can test you and say, we're not sure. I don't know. I'm just guessing. You know, I'm not a medical person. But anyway, I know there are tests like that. So it's a positive test only. So we just say may or may not. May or may not. We can't say for sure no. But it may or may not. So that's the first. Okay, so now, second test, theta equals pi over 2. How do we test theta equals pi over 2? That's negative r, negative theta, right? So take the original, r equals 3 sine theta, and put in negative r where you see r, and put in negative theta where you see theta. Good to there? Yeah, Rudy.
On that first test, I have r equals 3 cosine theta.
Right.
And I want to know why that's a yes.
Because that negative vanishes. Remember, for sine and tangent, a negative plugged in comes to the front, so that makes it different. But for cosine, negative plugged in, poof, gone. So then it looks the same as the original. So it's a yes. Yeah, only for cosine. Okay. Only for cosine do negatives plugged in vanish. For sine or tangent, they just come to the front. Well, we're not even doing tangent, are we? So for sine, they come to the front. All right, so now what's going to happen now? So I plugged in, everybody good there? I plugged in negative r for r. I plugged in negative theta for theta. And then I'm supposed to simplify. How does this simplify? What does that negative always do? Come for sine anyway. For cosine, it vanishes. For sine, it comes to the front. So like that. That good? And now what? Now what do you do? How else can I simplify this thing? Yeah, multiply both sides by -1, huh? It's got negative in both, so they're just going to vanish, aren't they? I'll show it formally, right? Because you can always do the same thing to both sides of an equation. That's always allowed. So it just becomes regular r is regular 3 sine theta. Is that the same as the original? Yeah, that's exactly the same as the original, isn't it? That's exactly how it originally looked. This and this are identical twins now. So that one's a yes. It has that kind of symmetry, doesn't it? This graph is going to be the same. The pi over 2, theta equals pi over 2 line is the y-axis. Whatever's on the right is going to be on the left for this graph. I don't know what is on the right and left. Well, I do actually. Huh? It's the 3 sine theta. It's the circle. So this one is going to be the same to the right and to the left of the y-axis, isn't it? Y-axis symmetry, or theta equals pi over 2 symmetry. Good. So really, you could have answered that question because you know what this thing looks like, huh? Well, no, be careful. You got to do the actual test because even though, yes, it does have that symmetry, you have to actually physically do the test, and the test may have said may or may not, even though we know in reality it has it because we know the picture. So you really got to physically do the test. Okay, so how about with respect to the pole? Pole's the origin. So for the pole, that's the origin. And for that one, we do negative r, just negative r. So take the original equation, r equals 3 sine theta, and boom, pop in negative r. Okay, and then try to simplify. Well, there's really nothing to do to simplify. And then they're asking, is this the same as original? The original is this. Are these guys identical twins? No. One's got a negative, the other does not. No, so it's may or may not, huh? May or may not be symmetrical through the pole. We know the graph, so we know it's actually not. Right? Remember the graph? It's like that. If you take any point, shoot through the origin, remember this is the origin, to the other side, there's not a point on the other side. It is actually not. Because we know the graph, we could actually say no. But the test just left us with a may or may not. But we know no, it does not. It is not the same other side of the origin on that one. Oops, now it's off the screen. That didn't. There we go. So yeah, so now, which of those 4 is the right one for r? Whoops, that's a funny looking r. For r equals 3 sine theta. Can you tell just by looking?
Yeah.
Because sine always goes on the y-axis. Boy, I've given you so much information, you don't even need to make any r theta tables, do you? My teachers made me do all these r theta tables. I spent hours plugging in r's and thetas. So let's do a little bit of that so you know where these. I don't want this to be too magical and mystical. Let me show you where it actually comes from. But yeah, since you already know, I mean, yeah, easy question, right? So, whoops, I just clicked on something funny and the whole thing went crazy. All right, so let's make the table and see why is it that r equals 3 sine theta ends up being that circle thing? Like, why is that the case? All right, let's do it. So what I'm going to do is I'm going to make a r theta table, like you would an XY table, and just get some dots. Okay, and I'm going to go over here. Okay, so there's our polar graph. We're going to actually use that to graph. Okay, let's go back now. So r theta, here we go. Just start with 0. No, actually, I'm going to start with theta. It's easier to plug in. I'm gonna make it theta r. It doesn't matter. Do it either way you want. But no, I think it's easier to make it theta r instead of r theta. So I'm gonna plug in 0 for theta first off. So r equals 3 sine theta. So 3 sine 0 degrees. So what's the sine of 0 degrees? let me also get the unit circle, wherever that is. Unit circle. Is that you there? Boom. Yes, good. All right, so there's the unit circle. So 0 degrees, here's cosine, here's sine. You know, the sine of 0 degrees is 0. Okay. There we go. All right, so this comes out 0. Good so far? Now, how much should we go up by? Whatever you feel like. Doesn't really matter a lot. How about, I don't know, how about 45 degrees? Well, how about I go a little slower? I'll do 30. I'll just do 30. All right, let's do 30 degrees, 45, 60, 90. How about I just do that? So 3 sine 30. So, okay, what's sine 30? 30 degrees, cosine sine of 30 is a half. So this is 3 times a half. Just use your calculator, 1.5. Just use decimals. 3 times a half, 1.5. Good so far. Everybody see what I'm doing? I'm just plugging in some theta angles. Bless you. And I'm just starting at 0, going up to 90 on the nice ones I know. So how about the next one? 3 sine 45 degrees. Well, what's the sine of 45? Here's 45. Cosine sine. Sine's root 2 over 2. So this is 3 times root 2 over 2. Hit the buttons on your calculator. Did I bring my calculator? 0.7. I think it's something. I don't know. I don't know what it is. 2.1. You don't need to be more accurate than that. I mean, we're graphing. I can't accurately graph more than 2.1. No, 2.12 would do nothing more for me. I can't really, not that accurate. So keep going. It's good enough. 2.1. 3 sine 60 degrees. Sine of 60 is, so here's 60. The sine is root 3 over 2, isn't it? The unit circle. And you can just hit the buttons on your calculator. This part, I believe this part will be on the calculator part. Yeah, so just hit the buttons on your calculator on this. Okay, and you get some number that I don't know. 3, 2. I'm getting 2.6. And then do 90. 93. Sine of 90 is 1, right? 90 degrees. You can't really see it up here. This is over 0 up 1. The sine is 1. So, again, just use your calculator. Just hit the buttons on your calculator. 3 times the sine of 90. Yeah, just use your calculator. This will be, I'm 99% sure this is, you can look on the price exam, which is online already. This is on the graphing, this is on the calculator part. So 3 times 1 is 3. All right, so I've got a bunch of values there. Now, there's more to come, but let's stop there for just a second. Let's put those dots on the graph before we go any further. All right, we ready? So let's go to my polar graph, and I'm going to put those on the graph one by one. In fact, maybe it'd be good just to bring the table right here. Let's just do that. Theta r, we did 0, 30 degrees, 45, 60, 90. And what values did we get? 0, 1.5, 2.1, 2.1, 2.63. Okay, so here we go. You guys ready? We're going to turn the cannon and everything, right? So first off, at 0 degrees, when the cannon's facing 0 degrees, you shoot out 0. Okay, well that's literally the origin, isn't it? You shoot nowhere. Next one, 30 degrees, 1.5. So aim at 30 degrees right here. Shoot out 1.5 lines. So that'd be 1, about right there. Everybody see what I did? That's at 1.5. Right? Because the 1 is the first circle, then 2, then 3, then 4 as the circles go out. They're counting 1, 2, 3, 4. So 1.5 at 30 degrees. Now at 45, 2.1. So at the 45 line, one just barely past 2. I'll just say that looks like about 2.1, Good. At 60 degrees, 2.6. So 60 degrees, 1, 2, a little past halfway, right? Like that maybe? 60 degrees, 2.6. 90 degrees, straight up, 3. Boom. Look at what it just did. So, and remember, we just did certain dots. There's all kinds of angles between 0 and 30. You could use your calculator and do 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, and just keep plugging them all in and getting a bunch of values. And what you would get is like that. They would all fill in and form that half of the circle. Make sense? And we already learned that this thing is symmetric, same, on the right and the left of the pi over 2 90-degree line. Remember, we proved that. We got a yes for that one. So whatever happens on the right, I don't even need to plug in values. It's got to happen on the left. We already proved it, that it's the same on the right and the left of the pi over 2 line. So there we go. I mean, we already knew it, but there it is by hand. That's how they got those results. That's how you see that's really true. Make sense on that? Questions? And notice it goes out to 3, doesn't it? And that was the number in the front here, 3. So this is r equals 3 sine theta. So whatever's in the front, that's the diameter, I guess. That's how far out the circle goes. It sits at the origin, goes up 3. Good, not too bad. R theta table. Any questions on that? All right. So let's symmetry. So let's go through that. So give it a try. So first off, with that equation, r equals 10 plus 10 cos theta, polar axis. First off, give that a polar axis. That's the x-axis. What do we plug in on that one?
Negative theta.
Negative theta. Plug negative theta in for theta. Yeah. So what's gonna happen? So we plug in negative theta for theta. So what's going to happen is we plug in negative theta for theta. What happens with cosine? What does cosine do? Vanish. Poof, gone. So because cosine's an even function. So it just becomes right there. How does that, is that the same as the original? Absolutely, huh? Here's the original. Here's this. They're identical twins. Someone's a yes. So that one's got, this graph is going to be the same above and below the x-axis, isn't it? That's the x-axis, the polar axis. So whatever happens on the top of the x-axis will be identical on the bottom. Okay. Let's go to question. All right, theta pi over 2 for r equals 10 plus 10 cosine. So theta equals pi over 2, what do we do with that? Both, huh? Yeah, both. So you put in negative r, you put in negative theta. So negative r is 10 plus 10 cosine negative theta. And as we know, when we simplify, that just vanishes. The negative just vanishes for cosine. So is this the same as the original?
Maybe.
Here's the original. Here's this. Are they identical twins? Well, right. So it says so they're not. It's not the same. So that's the may or may not case. Yeah. Good. Got that extra minus sign. It's not the same. So it's a may or may not be symmetrical to the line theta's pi over 2. Okay. Part C. Okay, so yeah, so for this one, r equals 10 plus 10 cos theta. What do we plug in to see if it's the same through the origin? Negative r, right? Because that means if you backfire and it's the same, then it's the same other side of the origin, isn't it? The same shooting through the origin. So you put in negative r, and you simplify, but there's really nothing to simplify. So is that the same as the original? No. So that's a may or may not. May or may not be this have pole symmetry, origin symmetry. Good. And now, so R equals 4 minus 3 cos theta. Let's try the various tests. Polar axis. So what do we do for the polar axis?
Bring it negative theta.
Yeah. Yep. Easy pickings now, huh? It's kind of the same thing every time. Look at negative theta. Gonzo. So is it the same as the original? This with this? Yes. It's identical. So it's a yes. So this one's going to be the same top and bottom of the x-axis again. So we just got to do the top, then we know the bottom's the same. See what symmetry does for you? It reduces half your work, huh? If you know it's the same top and bottom, just do the top. Bottom will be the same. All right?
I have a question.
Question.
When one of them is yes, are the other two always maybe?
I don't think so. You can't have a couple yeses.
Okay.
I don't know if we'll ever get that.
I see that pattern too.
How about almost always? But there's not a hard fast rule that says always.
And that would only be with cosine, not sine, because sine would.
No, sine would be a yes on the with the line data one.
Yeah, I wonder. You know what I wonder about is when we do the roses with the petals, because those are same top and bottom and right and left. Some of those are. So, but I wonder the test will tell us yes or maybe just a maybe. I'm not sure what'll happen.
I got one that was 3 maybes, but then, yeah, it was,
Okay, so sometimes you get all maybes.
but
Yeah.
then everything that was yes, the other two was always a maybe.
Okay. Yeah, probably that's usually what happens. So theta's pi over 2. What do? We plug in the both, don't we? Plug in both. So R equals 4 minus 3 cos theta. Plug in negative R. Plug in negative theta. So negative R, 4 minus 3 cos negative theta. So negative R, 4 minus 3 cos. The negative just vanishes. So is this the same as the original? No. So that's a may or may not. So with the origin, we plug in negative R. You backfire. So you backfire. There's nothing to simplify. Is it the same? Are those the twins? No. So again, it's may or may not, as you said. Okay, so now we want to graph. So let's go to the polar. Let's go to our polar chart. Make a theta R table. And R equals, what is it? 4 minus 3 cos theta. 4 minus 3 cos theta. Let's plug in some angles. 0, 30, 45, 60, 90. Probably need to keep going. We'll see. 120. Keep going. So plug into your calculator. See what you get. Get some values there. I'm going to do the same. I'm getting 1. It's good just to get a whole bunch of numbers first before you put anything on the graph. That way you know how big to make the jumps, right? If it goes up to like 20 and stuff, then I need to make the jumps 5 again. If it's just going to be 1 and 2, then I can make the jumps much smaller. So first get your values. And I'm getting 1.4 and 4 minus 3 cosine 5. I'm getting 1.9. 2.5. I'm getting 4. 120. I'll keep going. 5.5. So I did 120. I'll do 135. So 135. I'm getting 6.1. They're getting bigger. It's kind of funny. 150. I think I'm going to go all the way to 180. 1 minus 3 cosine 150. I'm getting 6.6. They just keep getting bigger. They're slowing down though, looks like. And then 180. Maybe I should do 165. I don't know, whatever. I'll go back and see if I need more detailed information or not. I'm getting 7. Okay. So there. So it looks like it goes out to 7. So I can just use these things by ones. That'll be kind of perfect. Don't we have 7? 1, 2, 3, 4, 5, 6, 7, 8, 8. Yeah. So it's perfect. Okay. So here we go. Let's fire the cannon question.
What does it look like when you have an inner loop because the angles will have 2 points on the
They also have 2 points.
on the inside?
I don't know. Let's graph it, and then maybe we'll add some light to that question. But feel free to bring it up again if I'm not answered it by the graph. So let's start at 0. Aim the cannon at 0. Shoot out 1. So here's the first dot. Aim the cannon at 30 degrees. Shoot out 1.4. So 1.4, about right there. A little less than, between 1 and 2. A little less than halfway. Aim 45. Shoot out 1.9. So that's almost 2, just below 2 at 45. Aim 60, shoot out 2.5, 1, 2.5 right here. Aim 90, shoot out 4, 2, 3, 4 right there. So far so good, it's going like that. Aim 120, shoot 5.5. So 120, 1, 2, 3, 4, 5.5 right there. 135, 6.1. So 1, 2, 3, 4, 5, 6.1, just barely past the 6 mark. Like right there. And 156.6, be about right there, a little past halfway. And 180, all of a sudden it's at 7. No, that's 8, huh? So 7, is that right? 1, 2, 3, 4, 5, 6, yeah, 7. All right, so it's kind of going like this. Well, it's not so rounded there, but it should be more rounded than I've got it. What was the 120? 5.5? So I didn't do that very well. Right there. Okay, so there's like that half. And then the other half has to be identical. Above and below is identical, isn't it? Above and below is totally identical. So I'll just copy it. It's going to do the exact same thing, which means it's going to kind of come out. Well, here, let me do this. 1, 2, 3, 4. So 1, 2, 3, 4. So it'll be right here. I'll just do some of the crucial points. It's going to kind of, whoops, come on. Come out like this and sort of come around and boom. Like that. Right? We learned it was symmetric above and below the x-axis, the polar axis. So there we go. Is that what they predicted by the little table thing we had?
There's supposed to be an inner loop.
There's supposed to be an inner loop?
Yeah.
There is.
Let's go. All right, so maybe I'm just going to go through it fast. I think you guys are quick and good at this now. So try that one. So first thing, to have polar axis. Polar axis is, what is that? Negative theta. Plug in negative theta. 6 cosine 4 times negative theta. Negative just comes to the front. Oh, no, vanishes. Negative vanishes for cosine. Negative vanishes. Is that the same as the original? Yes, it is. That's a yes. So I'll just do those quick. So the other two came out maybes. Let me just do it quick. So for the r equals 6 cosine 4 theta, you put in negative r and negative theta because we're doing line theta's pi over 2, y-axis. So then we get negative r 6 cosine 4 times negative theta. The negative in here vanishes, but the negative in the front stays. So same, no. And then the last one would just take r equals, so this would be c now, r equals 6 cosine 4 theta, put in negative r. So negative r is 6 cosine 4 theta. Is that the same? No. So that's why those are both maybes. On to the picture we go. So let's graph that thing. 6 cosine 4 theta. What are we expecting? Yeah, remember when you have a 4 theta, like you have something plugged in, you're going to get some kind of petals, right? How many petals? 8 petals. That's got to be challenging to graph. 8 petals. Because when it's even, when you plug in an even thing, you double it. If it was odd, if that was 5 theta, there would just be 5 petals, right? If it's odd, it's the same number. It's even, it's double. So there's going to be 8 petals. Let's plug that into our polar work. So what's our equation? R equals 6 cos 4 theta. So I'll do a theta R equals 6 cosine 4 theta. Plug in 0. Plug in 30. Plug in 45, 60, 90. Let's see what we get. Let's crank out some numbers there. Oh, you know, we're going to need to go smaller. Yeah, guys, on this one, and gals, we need to go as small as we can because the action is going to happen fast. The things will change quick. So instead of, I'm just going to do 0 first off. Cosine of 0 is 1. I'm going to get 6. So it's 0, 6, 1, 2, 3, 4, 5, 6. Boom, there's the first dot. Aim the cannon at 0, get a 6. Plug in 0 there, it comes out 6. Now, I'm just going to go 15 degrees. If you plug in 15, use your calculator. 6 cosine. Now, 4 times 15 is, what, 60? So then that comes out 3. So at 15, it's back here at 3 already. And then at 30, at 30, yeah, something bad's going to happen. Well, I mean, we're going to miss something is what I mean. You're going to be at negative 3. Did y'all get that? Aim the cannon this away, 30 degrees, and it backfires 3. It backfires 3. 1, 2, 3. Do you see what just happened there? Maybe not so much. Let's hold the show for a minute. Something kind of weird's happening. Everybody see how I got those values first off? So, if you wanted to draw this thing, what does that mean happened? Well, really we missed a value. I know this because I know when is it going to hit 0? What makes cosine 0? Cosine of what angle 0? 90. Cosine of 90 is 0. So you see, whenever 4 theta is 90, whenever the inside of the cosine is 90, it's going to be 0. It's going to hit the origin. Fire nowhere. Origin. So what makes that happen? Divide by 4. 22.5. At 22.5 degrees. See, I skipped over because I just went from 15 to 30. Between those two, at 22.5, plug it in your calculator if you're not sure. Plug in 22.5 times 4 will be 90. Cosine of 90 be 0. 0 times 6 is 0. So it really we missed at 22.5, you get a 0. And then at 30, you get that negative 3. Now, what does that mean happened? At 22.5, it came back to the origin. So what am I saying is going on? I'm saying that we started to draw this thing. It went. Here's how you would draw it. If you were real time, like on some online program that would draw these things for you, I'm sure you could type into Google and have it up in seconds. Some real time program that would draw these polar graphs in real time. Here's how it would happen. It would start going like this, and it would shoot back to the origin at 20 before it got to 30 at 22.5, and then what's it going to do? It's going to shoot to the other side. It starts drawing back here now. So it's going to draw the 8 petals, but it's not going to do them 1, 2, 3, 4. It's going to do one here, one back there, one up there, one down there, one up there, one down there. It's going to weave back and forth is what it's going to do as it draws the 8 petals. Does that make sense? That's how it's drawing the 8 petals. It's one smooth, continuous operation. It's just out here, down here, it'll come back, it'll go up there, it'll come down here, it'll go just like an ice skater, just smoothly cranking out the pedals. That's what it's going to do. So now you don't have to find the 22.5 thing, and you don't think, oh, I got to figure all that. You don't have to. I mean, just know that whenever it goes negative, it went through the origin, somewhere in between, and just go ahead and draw your line through the origin to get to that negative spot. Just know it happened. It doesn't magically go from positive to negative. This is a smooth operation. It doesn't skip spots. So it's a continuous function, we call it. You'll get more into that in calculus. So after 30, now I'll just go on to 45. Type in 45. What is that? 180. Cosine of 180 is negative 1. Negative 6, I think. So 45, when you aim the cannon at 45, it's going to shoot back 6. So that's going to be 1, 2, 3, 4, 5, 6 right here. So see what it's doing? It's drawing this branch. Keep going. So it's basically going to complete this branch. If we keep going, it's going to go 60, 240, 6 cosine 240. I'm going to get negative 3. So it's 60 degrees. It's back at when facing 60. It's going to shoot back, fire backwards 3, 2, 3 right here. There it is. It's completing that branch now with backfires. And then when you get to 90, 360, cosine 360, 0, cosine, I mean, it's cosine 0. Cosine 0 is 1. It's going to be 6. And 90, all of a sudden, it's up here at 6. What happened? Really quickly, it shot through the origin and then went up here. It just happened fast. Am I doing that right? Yeah, that's right. That's still true. See what happened there? I went from this. The trick is, how did it go from this dot at 60 to this dot at 90? Well, it must pass through the origin. If you did values in between 60 and 90, 70, 75, 80, you'd see it's going dot, 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 quickly shooting through the origin and making another branch, another petal. So it's just going to keep going. It's going to make all these. We're going to make 8 petals in the end. Could we now just finish the rest of the graph? Now that we know there's 8 petals, because it's cosine 4 theta, and we know there's going to be 1 here on the x, 1 clearly on the y. This graph, we already determined, is the same top and bottom of the x-axis. So there's 1 up, there's 1 down. And if there's 1 right here, there's 1 right there. That's only 5. That's weird. Where's the other ones? I don't know. I don't want to keep playing with this forever. You could just keep plugging in points and plugging in points, and it would just keep drawing out the different branches. Maybe I should have got an online program up. So yeah, I should have known there's going to be a branch right here, isn't there? So what's that? 1, 2, 3, 4, 5, 6, and then a branch here and a branch here. And it would draw them all out as you plugged in points. Because we need to see how those inner loops are made. We've had a dimple, but we've had a cardioid, the heart, but we've not had the inner loop. I believe this will be the inner loop. So let's go through the 3 tests first off. So r equals 1 minus 2 sine theta. Put in negative r. Oh, no, not negative r. Put in negative theta. For the first test, for the polar axis test, the x-axis, positive and negative theta, above and below the x-axis. When you plug in negative theta to sine, it moves to the front. Just of that sine. Just to the front of the sine, not at the front of the 1, right? Just in the front of whatever's on the sine. So it become 1 plus 2 sine theta. Does that make sense? And so is that the same? No. These are not identical twins. It's a may or may not, huh? I think this one's going to be all 3 may or may not. Is this the one? Yeah. It's probably going to be all 3 may or may not. So that's a may or may not. That good? Didn't come out the same as the... Okay, so the second one, take r equals 1 minus 2 sine theta, and we put in negative r and negative theta, negative r. Yeah, this might be valuable for you to see why this actually comes out no, because you might think at first it comes out yes, it does not. Put in negative r and negative theta, we get negative r, 1 minus, and what does that negative do? Comes to the front of just the sine, so 1 plus 2 sine theta. Is that the same as the original? No, the original has regular r, this has negative r. There's no way to make them the same. If you multiply both sides by, you might think, well, can't I just multiply both sides by -1? No, you'd have to multiply all of that by -1. You'd get r, then it would be -1 minus 2 sine theta. And that's not the same either. There's no way to simplify it and have it come out to be the same as the original. It never will. So it's a no. So it's a may or may not. You know, there's no way to do that. So next, final test is the pole. So you take r equals 1 minus 2 sine theta, and you put in -r. And you ask the question, is that the same? And the answer again is no. All right, so it's all may or may not, may or may not, may or may not. Okay, and so what is our equation? R equals 1 minus 2 sine theta. So let's do it. Theta r 1 minus 2 sine theta. Let's put in 0, 30, 45, 60, 90. Let's just plug them in, see what happens to our values here. So this is going to be 1 sine 30 to half. So that's going to be 0. 45, I don't know. 1 minus root 2 minus, I think it's minus 0.4. Sine 60, I don't know. So maybe it's minus 0.7. Sine 90 is 1 minus -1. Those coming out right? I'm sort of eyeballing them. Those right? You getting those, Winnie?
I got some of them. You go fast.
All right, yeah. So let me know if I messed up on any of those. I think those are right. I'm gonna put those. Now, it's not going out very far, huh? So why don't we do this? Why don't we? Because if I just make the marks 1, the graph's going to be like all in here, and I can hardly even see it. You know. So let me make the marks. What? 0.2. Is that confusing? Can I make them 0.2? Because say the first line is 0.2, and this is 0.4, 0.6, 0.8, 1.0. Is that okay? Just so we can see it more, kind of magnify it a little bit. So, okay, so aim the cannon at 0, shoot out 1 right here. Aim the cannon at 0, shoot out 1. Aim the cannon at 30 degrees, shoot out 0. It came right on back in a big hurry. Maybe I should test in between. Maybe I should have done 15.
You
What?
need 0.5.
Is that what it is? You did 15? Yeah, if you plug in 15, you get, what is it, 0.5?
Yes.
0.5. So at 15, it was 0.2, 0.4, 0.6 will be right here. So it looks like it came back like that. Good so far? It is good to do that 15. Okay. Now, keep going. 120. Plug in 120. I don't know. Are those values right? Am I getting anybody checking those on the calculator?
Yeah,
They're good. Okay. Thank you. 1 minus 2 sine 120. Negative 0.7. So what does that mean now? The negatives are always kind of where it's backfire, huh? Oh, wait. I didn't. What am I doing? I haven't even done these yet. What am I doing? All right. 45 backfire 0.4. So when you're aiming at 45, aim the cannon at 45, it backfires 0.4. This is the backfire direction. 0.4, 0.2, 0.4 right here. Remember, every line is 0.2. So 0.4. So it did this, didn't it? Now it doesn't go. You might wonder. Let me help. You might wonder, Mister, why are you doing curved? Why is it just? It's boom straight there. Well, no. Remember, I'm jumping from 30 degrees to 45. So the cannon is sweeping out angles from 30 to 45, and it's firing continuously as you go. It's a machine gun, right? So it's a machine gun cannon. It's firing out all kinds of values. I'm just jumping ahead in time. So if it got from here to here as the cannon swept from there to there, it must have fired all around there, right? It must be doing the same thing. It's a continuous function, smooth. There's no jumping. So, yeah, so it must be doing that. Keep going. 60 minus 0.7. So when you're aimed at 60, it backfires 0.7, 0.2, 0.4, 0.6, 0.7. So it backfires there. When you're aimed at 90 straight up, it backfires 1. 0.2, 0.4, 0.6, 0.8, 0.1. I mean 1.0. It's kind of weird. So aimed at 90, it backfired 1. All right, let's keep going. Aim at 120, it backfires 0.7. So aim at 120, 2 lines off, 2 lines, it backfires 0.2, 0.4, 0.6, 0.7. Right there. Tracking with me? We had no symmetry that we knew of, huh? So keep going. I can't do any symmetry things. 135, so I did 120, 135 now. Plug in 135 minus 2 sine 135. And I'm getting a backfire of 0.4. So 135, you're aimed this way. It backfires 0.4. So 0.2, 0.4 right here. It's coming in. And 150. So 1 minus 2 sine 150 is 0. So it comes into 0 like that. Let me get rid of all these arrow things. We good so far? Keep going. What's after 150? We could do 165. Maybe that'd be helpful. I don't know. 1 minus 2 sine 165. I'm getting 0.5. So, yeah, 165, it shoots out 0.2, 0.4, 0.5 right here. So it's swept through the origin. It's up here now. Hasn't it? Is this weird? This seems different than I'm expecting.
It's on a much smaller scale than you're thinking.
Okay, well, I'll just keep going. Hopefully something good will happen in the end. 180. So, yeah, it's just a big loop. Is that what it is? 1 minus 2 sine 180. I'm getting 1. So at 180, it shoots out at 1.
Keep going all the way around, something like that.
It's 0.2, 0.4, 0.6, 0.8, 1. Boom, like that. Yeah, yeah. Keep going. You could do 195. It's probably going to be, well, I don't know, 0.5. Yeah, 1.5. Wait, oh, no. Yeah, no, that's why, yeah, 1 minus 2 sine 195.
Let's sweep all the way back around to the other point. That's what it's going to do.
What if I got 1.5, 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4. I got one way out here. It's like going out further. 1.5, I didn't expect that. All right.
2 is less than 1, so it's an inner loop.
Okay. 210. 1 minus 2 sine 210. 2. At 210, it's at 2. Do I even have 2 on this graph? 1, 2, 3, 4. There's 1. 1, 2, 3. Man, it's kind of out here. It's going off my graph. Right, let's put it out here. At 225, hopefully it's coming back now. Come on back. No, it's going more. 2.4. I didn't really, it's just shooting out here. Even further. I'm getting tired of doing values. All right. Yeah, well, it's too much magnification. So that's the inner loop?
Yeah.
Oh, that's a problem. I see. All right, I've seen enough. I get it now. Yeah, so it's coming way out here, and that's the inner loop. Yeah, I didn't realize it would start with the inner loop. That was not what I just kind of assumed the inner loop would be at the end. But it started with that's the inner loop, and then it's going to do some big loop down here, isn't it? It's going out and out and out. All right, so there we go. And it's sine, and, so it's on the y-axis, and it's negative sine, so it's down, huh? It's down on the y-axis. I hope you enjoyed that. That's it. Questions on that? Doing those? Did I answer your question? Okay. All right, so...